exam is coming up on on Wednesday this week. So it will be here in lecture. You'll have the entire hour and 20 minutes to work on it. And it will cover the first 3 chapters that we've talked about since the first day of the semester. So namely, the conjugated dienes and Diels-Alder, the aromaticity, and then the benzene reactions that we were talking about last week. So before we get back into the new material, does anybody have questions about the exam or anything else for that matter?
So that's lab 1 and 2, right? I mean, experiment 1 and 2 with the exam.
Yeah, I'm not going to test you directly on any of the experiments. I mean, part of it will kind of fall in because you did a Diels-Alder reaction and you did the nitration reaction. So, I mean, kind of by accident you'll be tested on it, but I'm not going to pull anything directly from the lab into your lecture exams. Okay. Any other questions?
Are we starting experiment 4 on Wednesday?
We'll actually start. We're not going to do experiment 4. We're actually going to start experiment 5. And it's a techniques lab. It's on column chromatography, and so there's no pre-lab needed. So, yeah, that should free up a little bit of time for you anyway. Any other questions? Okay, then why don't we go ahead and get started. See if I can manage to get this recording. Okay, so last time we had stopped, we were talking about mass spectrometry. And just to kind of quickly review here, when we are performing mass spec, it begins very GC-like. In fact, very, very commonly, GC and mass spec are used in tandem. It's a very powerful method of separating and characterizing mixtures. So, but in just the mass spectrometer, you inject your sample into a small oven. The sample gets vaporized at high heat. Those vaporized molecules get bombarded by that very high energy beam of electrons, which ultimately serve to eject an electron from the molecule. What that results in is a molecule that has both a positive charge and an unpaired electron, what we call the radical cation. We also refer to that as the molecular ion or the parent. And because it is charged and the flight tube is surrounded by a very strong magnetic field, those charged particles, those cations, get accelerated through the flight tube. Occasionally, those ions of the molecule, the molecular ion, will reach the detector, and you'll see a peak that corresponds to the molecular weight of the compound. The vast majority of them, however, due to that very high amount of kinetic energy imparted by the electron beam, they end up just blowing apart, or fragmenting, we call it. And so you end up getting a whole host of different fragments of that molecule. And based on the fragmentation, we can tell a lot about the structure of the molecule. Okay? And again, no two molecules have the same mass spectrum, so it becomes essentially a molecular fingerprint. And if you have a database, you can compare unknown mass spectra to known compounds and ultimately arrive at the identity of that particular species. So it's an incredibly powerful method of unknown identification. And so what we're going to do today is we're just going to go through a few of the more more important functional groups and look at how they commonly fragment. Remember, we're forming cations here. And so the mass spec is going to, these molecules are going to fragment in fairly predictable ways in order to give us more stable carbocations. So you've already learned a lot about carbocation stability. You talked about that a lot last semester. So we're going to kind of just extend that conversation here in the context of mass spectrometry and trying to use that in order to predict fragmentation patterns. Okay? So one note about fragmentation that I know we talked about the last time is when you have a fragmentation, these are always going to, so kind of just abbreviate like this. So this would be the molecular ion of a generic molecule. Again, sometimes those are going to make it all the way through the detector. Oftentimes they will not, however. And so when this fragments, what you're going to see is you always get two pieces. Every fragmentation gives you two pieces. You're always going to see a cation part, and you're always going to get a radical part. And these can fragment in both ways. So this first fragmentation that I've done here, I've called the R my cation and my R prime the radical. You could also get the other way. I could get the R as my radical and the R prime as my cation. Okay? Now the thing to remember is due to the magnetic field that is associated with the flight tube, you are only ever going to see the plus charges. Radicals are invisible because they never make it to the detector because they are not accelerated through the flight tube. So here is a fairly simple mass spectrum of 2,4-dimethylpentane. And this has a molecular weight of 100. And so you can see right here at 100, we have a fairly small molecular ion that corresponds to the radical cation of this, making it all the way through the flight tube and to the detector. You can see, however, that it is a relatively small peak. The vast majority of the things recorded by the detector are fragments of that species. Right? And you can see you've got some fairly major ones. You have an 85 peak here, you've got a strong 57, 43, and 41. The 41 is the most abundant peak. The instrument automatically kind of sets that to 100% and then ranks everything relative to that. Okay? So this is what we call the base peak. Now, if we're looking at the structure and you're looking at some of the more prominent ions, what do we think this 85 comes from? Now, that would be, sometimes it's useful to think about these things in terms of the loss. So if you're talking about 100 as a molecular ion, this peak at 85, that corresponds to a loss of 15. So what could that fragment be? What would correspond to a 15 massed fragment?
Methyl.
Yeah, methyl group, right? It's a CH3. And that would make sense. I mean, you've got a bunch of different methyl groups in this molecule. Here, 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 here. So it would not be unreasonable to think that you could lose a 15 mass fragment or a methyl group. And that's just simple math using the periodic table, right? Carbon is 12, each hydrogen is 1, so 12 plus 3 is 15. That would be the methyl group, all right? And you're going to get familiar with some of these more common fragments. For instance, a methyl is 15, ethyl is 29, propyl or isopropyl is 43, the butyl is 57. So as you start working through this, you're going to start to just kind of recognize some of these more common fragment ions just by their masses. Okay? So, as I said, what we're going to do is we're going to go through and we are going to kind of look at some of the more common functional groups and look at their expected fragmentations. And we're going to start this with the straight chain alkanes. Now, the first part is always going to be the same, right? You're going to take whatever molecule you're interested in, and you're going to hit that with that high energy beam of electrons. And as we said, that's going to eject one of the molecule's electrons. In a case like this, I really have no idea which electron is going to be lost, nor do I really care. The reason I don't really know is because all of those electrons are very similar. They're all sitting in sigma bonds. So it's not really the case that one of these is going to be more likely to be lost than any of the others. All I know is that one of them is going to be ejected. And so in a case like this, where I really have no clue as to which specific electron is going to be lost, I'm just going to abbreviate kind of over the molecule, just give it a plus dot notation, indicating that this thing has lost one of its electrons. I don't really know where, but it's gone, okay? That's not going to be the case for all functional groups. As you'll see, as we start making our way through, some functional groups, I'm going to know exactly which electron is going to be lost, because not all electrons are the same, right? Some electrons are more tightly held than others. And when you eject an electron, you're going to lose the one that's easiest to lose. It just so happens that in this particular example with these straight chain alkanes, all of those electrons are pretty similar, and so we don't know, right? So when we think about that, the straight chain alkanes, there's not a whole lot to say about them. They typically give kind of bell-shaped curves, or offset bell-shaped curves. And you tend to see prominent peaks at units of 14. Because really, the only thing that this thing can do is kind of chunk off methylene by methylene by methylene. That's really the only way it can fragment. So you tend to see kind of bell-shaped curves, and the major peaks tend to be in units of approximately 15, or 14 rather. So if we have a look at this spectrum, there's the mass spec of pentane. You can see that the molecular weight of pentane is 72, and you do indeed see a small molecular ion here. Other major peaks are kind of in that kind of bell-shaped curve here, but they correspond to simply losing carbon groups. Right, so your first major peak after the molecular ion is 57. That corresponds to a loss of 15, or a butyl fragment. The next major one is 43. You can see that's our base peak, which corresponds to the propyl fragment. And then your next one is at about 29, which is your ethyl fragment. Okay. Now, does it make sense to you why the ends of this are relatively small peaks? Why is it that the propyl is such a intense, abundant peak, whereas, say, the butyl or the methyl is such a small, minor peak? Sometimes it's useful to think about what's lost. So if, I'm going to go ahead and draw my other fragment. So if we lost if we're getting a butyl, then the other piece of that fragmentation would be the methyl radical. Because remember, every fragmentation gives you two pieces, a cation and a radical. So if my cation is butyl, then the radical would have to be the methyl, because otherwise I wouldn't have the right number of carbons for this molecule, right? Similarly, if we go down to the other end, if we're saying that the methyl is my cation, then that means that the radical would be the butyl radical. So what is it about these two fragmentations that are not particularly favorable?
I don't know if this is, well, when you're trying to break a stick, it's easier to break it in the middle. Is that kind of related?
That's a good point. I never really thought of it that way, but that is interesting. Think about your stabilities. Is one of these particularly bad in terms of its intermediate stability?
Methyl is going to be.
Yeah, what do you know about methyl cations?
It's not even primary, right?
Right. Yeah, in terms of carbocation stability, a methyl is the worst you could possibly get. Remember, the more highly substituted the carbocation, the more stable the carbocation. The methyl has 0 substitution on it. So it is the worst in terms of its stability. Well, then what about this? I mean, this is a primary carbocation, so that's a lot better than the methyl. But look at your radical. Every fragmentation involves 2 pieces, and you must consider both of those pieces. Well, radical stability just so happens to trend with carbocation stability. So in the same way that the more substituted the carbocation, the more stable the carbocation, well, the more substituted the radical, the more stable the radical as well. And so this is giving you a methyl radical, which again is the worst possible scenario. So these fragmentations that give rise to either methyl radicals or methyl cations are going to typically be quite minor because those intermediates are quite unstable. Right? Take-home message to this is the more stable the fragment, the more abundant that fragmentation will be. Right? Any questions on that? All right, so there's not a whole lot to say about these straight chain alkanes. So let's just move on to something a little bit more interesting. Let's look at the branched chain alkanes. So in the first step of this, it's going to be like the first step of all of them, meaning that you're going to hit this molecule, this branched chain alkane, with a high energy beam of electrons, and it's kind of small on the slide, but you're going to generate the plus dot. Okay, just like the straight chain alkanes, I don't really know which electron is going to be lost because, again, all of those electrons are in sigma bonds and they're very similar. So I don't know where it's going to be lost from. I just know it's going to be lost. So I'm indicating it with a plus dot to say one electron got lost from somewhere. Now, when we start imagining how this is going to fragment in the flight tube, here we get a case where not all those fragmentations are equal. You know, it would be theoretically possible for me to come in and slice off a methyl group. But it wouldn't be particularly likely. You know, I wouldn't expect it to be one of my more abundant peaks because, again, methyl radicals or methyl cations are not very stable. And especially when you have other options, which you do in this molecule, you know, I've got kind of 3 better, much better options for fragmentation here, right? And these are a lot better because they involve more highly substituted radicals and cations. Okay, so I need a calculator because my math is, well, not the best. So if we're looking at this 2,3-dimethylpentane, this has a molecular weight of, where was it, 100. So we could go through and figure out what these different fragments are going to be, they're going to weigh. So let's see. In this first fragmentation, you can see we're losing a ethyl radical that has mass 29. And so my math is correct. We take 29 from 100. This cation, which we would expect to see at 71. Okay, what else? So the second fragmentation, we're losing a butyl, which is a 57 fragment. So that would mean that isopropyl cation should be a 43 mass. And then we're splitting it the other way. Again, this isopropyl is 43. That means we would expect a cation fragment of 57. All right. And all of those are a lot better than a simple loss of a methyl group. Not to say you're not going to see a peak at 85, but we would expect it to be quite small, especially relative to these other fragmentation patterns. All right, so let's go ahead and have a look at the spectrum here. So here we are. You can see we do have a small molecular ion there at 100. Notice you do have a small loss of methyl here. So we do have that fragmentation that gives rise to the methyl radical here. But it's not very abundant, right? The loss of the ethyl group giving the secondary cation is a lot stronger, 71. You can see your base peak, you've actually got two base peaks in this one, corresponding to the butyl cation and then also the isopropyl cation. Right? Both of these are fairly strong because they give rise to two secondary products, a secondary cation with a secondary radical. And then again, see, you do have a 29 peak, that would be that ethyl cation, and there at 15, the methyl cation here is almost imperceptible. Okay? But again, the more stable these fragmentations, the more prominent they'll be. All right? And the other thing I want you to pay attention to is notice, this is kind of like IR in the sense that if you look at an IR spectrum, you don't go through and try to identify every single absorption band. Right? In the same way, you're not going to look at a mass spectrum and try to identify every single peak in the spectrum. Okay, just kind of, you learn the more predictable fragmentation patterns for the functional groups, and you kind of look for those. Okay? So the next class, don't worry about. Have cycloalkanes. You can forget about that. Just scratch out the slide. You don't need to know anything about that. What I want to go to now are the alkenes, because these get a little bit more interesting because I can predict what electron I'm going to lose here. Because the alkenes have two different types of electrons. They have the sigma electrons, the electrons of the sigma bonds, and then they have the electrons of the pi bonds. And as you know, the pi electrons are farther from the nucleus, are less tightly held by the nucleus, and so they are easier to lose. So when we subject this to that high energy beam of electrons, I would predict that I'm going to lose one of those pi electrons over one of the sigma. And so what that's going to result in is a species that kind of that radical cation. See, I've essentially broken the pi bond. There's one electron left, and I've put it right here on this carbon, and then this guy is electron deficient, so it's now a positive charge. Okay? So whenever I go to do fragmentation, we're going to do a homolytic cleavage. You can see that shown. Let me just draw it back. So one electron is going to go there, and one electron is going to go there. So we're going to cleave off the methyl radical, and what that leaves us with is, if you imagine just kind of following the electrons, what it would look like initially would be that. Of course, that's kind of a weird way to draw a cation, and so instead we'll just represent it like this. And do you see why that would be such a favorable fragmentation? What's particularly stable about that?
It's resonance stabilized.
Yeah, exactly. This is it forms doing these what we call allylic cleavages, meaning cleaving one carbon away from the double bond, gives rise to these allylic or resonance stabilized cations, which are quite stable. All right, so typically when you look at an alkene, what you're going to be looking for is what are the fragments I can cleave that are going to give me these very good resonance stabilized allylic carbocations. All right? The other type of cleavage that you'll commonly see, not quite as strong, is a vinylic cleavage, meaning you cleave at the double bond. So for instance, if you had this radical cation again, instead of cleaving one carbon away, we're going to cleave at the double bond, and that results in these vinylic cations. Okay, again, a vinylic cation is not nearly as good as an allylic, but you do see these pretty regularly. All right, so So let's have a look. We'll look at a couple different alkenes. There's that one butene. Let's put some masses in here. Oh, we've got a 41 and 27. So you can see with the alkene, you actually have a good, strong molecular ion, which is fairly common for these types of functional groups. Alkenes give good, strong molecular ions. At 41, that is your base peak. Again, that corresponds to that allylic cleavage. And then your other strong one is here at 27. So that would be that vinylic. Okay. All right, let's have a look at a slightly more complicated alkene and see what we can do with that. So let's do 4-methyl-2-hexene. So that's what we're going to look at. The first step of the process is the ionization. So we're going to knock out one of those electrons. So our cation should look something like, I think I want to do it like this. So that's going to be your radical cation. And from here, again, we're just going to try to cleave in order to get those resonance stabilized cations. So I could maybe, I guess you could lose the methyl group there, which is going to give us that kind of a pair. What else could we lose? We could lose probably that ethyl group. Which would give us that cation and that radical. And then I guess the only other thing we could do is do one of those vinylic cleavages, which would give us that pair.
Where did that one go? Where's the wiggle?
The purple one? This one? From the vinylic cleavage.
Right here.
What about the first one? Just off there?
The red one?
Yeah.
From the loss of that methyl group.
And why it became double bond?
Oh, that's not a double one. That's sorry, it's my bad artwork. That is a single bond.
No, I meant the red one. So how it became a double bond on that side?
Because if you cleaved off that, let's do it like this. If you do that cleavage, what you would initially get is the methyl CH3 dot coming off, and you would end up making, so we have the dot there. Initially, if this does a homolytic cleavage, you would end up with a dot there too. And so normally we don't draw diradical species, we just kind of put them together in a pi bond.
Okay.
And that's what you see represented right here. Okay. All right, so in terms of numbers here, this has a molecular weight of 98. So if we did that first cleavage, we would have, again, that's a methyl, so that'd be 15, 98 minus 15. This should be an 83 fragment. The 98 loss of ethyl should give us a 69 fragment. And then the 98 loss of butyl should give us a 41 fragment. Okay. So those would be my expected fragmentations. We can go ahead and look at the spectrum, see what we can find. With the alkene, again, we see a fairly strong molecular ion. Here is your 69 fragment. That is that base peak. That's your one of your strong allylic cleavages. There at 41, that would be your vinylic cleavage. And then, what's our third one? Oh, that 83. Your 83 is here, but it's really weak. Does that make sense? Why, the 83 is technically an allylic cleavage, but it's a fairly weak peak. Why would that be?
Because the methane, or the methyl's not gonna be very stable.
Yeah, look at your radical here. Remember, any fragmentation, you have to look at both components, both the cation and the radical. So this is giving you a very stable cation, but the radical is pretty bad, right? And as a result, you don't see that fragmentation as a very abundant one. Okay? Any questions on the alkenes? All right, then let's move on. We're gonna look at the benzene compounds now. The benzenes will cleave in a very similar way to the alkenes. And just like the...
Can you go back a little bit, take a picture of it?
Oh, this one, the spectrum or the...
No, yeah, thank you.
Okay, so the benzene compounds are going to fragment in a very similar way to the alkenes. So when this gets hit by the high energy beam of electrons, again, because I have two different types of electrons in the molecule, namely the electrons of the sigma bonds and the electrons of the pi bonds, I can predict where I'm going to lose the electron. And as we saw before, you're going to lose it from the less tightly held, which are the pi electrons. And so when this gets hit with the high energy beam of electrons, you're going to fragment. I have my positive charge here, and I put my radical there because these are going to tend to do what we call benzylic cleavages. All right, so meaning we are going to cleave that bond just beyond the benzylic position. All right, and so the point of that, again, these are going to be homolytic cleavages, and so one electron goes there, one electron goes here, and again, if you were just to kind of draw those electrons in, what you would see is you would have dot there and dot there. And again, we don't usually draw these diradicals, just connect them through a bond, but you see what's particularly favorable about these benzylic cleavages. I can, through resonance, kind of move that positive charge throughout the ring, right? That's a very highly stabilized cation. And so that's what happens whenever you do the benzylic cleavages. You get those very stabilized benzylic cations. The other thing that these benzene compounds do is just kind of lose the side chain altogether. So I've got a propyl group here attached to the ring. You can just lose the entire propyl group. These give a very highly diagnostic peak. So they're not typically very strong, but the fact that it's there, if you see a 77 fragment, you automatically know you're dealing with a benzene compound, because that's the only thing that shows up around that region. So again, not usually very strong, but the presence alone tells you a lot about your structure. All right, so we can have a look at propylbenzene. Oh, actually I don't have that. Let's do sec-butylbenzene. So we can do this. Again, when you hit that with a high energy beam of electrons, we're going to eject one of the pi electrons to give us a cation that looks like this. Plus charge there, and the dot there. And from here, what we're going to try to do is just do the benzylic cleavages that are available. So I could cleave, I guess, the methyl group there, which is going to give me that plus methyl dot, or we could cleave the ethyl group. Both of those would be benzylic cleavage.
both benzylic, you said?
Mm-hmm. Both those benzylic cleavages. Which one do you like better? Red or blue?
Blue.
Yeah, the blue. I mean, the cations are essentially the same. Both of them are resonance-stabilized benzylic cations, but in terms of the radical, this is a lot better than this. And so on that basis, we would probably predict this to be a much stronger fragment. The other thing that this can do, as I said a minute ago, is you could just lose the whole group, which is going to give you that 77 fragment. So the first one, let's see, 134 minus 15, that's a 119. But probably the biggest one is going to be that 134 minus the 29, which is a 105. That would be my bet for the base peak. So if we have a look at that spectrum, you can see there at 134, you've got a pretty good molecular ion here. At 105, there's your base peak. There's that good benzylic cleavage. And then what was the other one that we said? The 119. Barely. Right? But again, not terribly surprising because that 119 corresponded to the benzylic cleavage that gave the methyl radical. And then finally, do we have a 77? Yeah, right here. So again, you can see it's small, but the presence of it alone tells you a lot about the molecule. It tells you you've got a benzene. Okay. Any questions on these?
I'm sorry, can you scroll back up? So
Yep.
This is 119.
Yep, the 119 right here.
Sorry to ask that, but how do we get those numbers again?
Just doing subtraction. So I know that this compound has a molecular weight of 134, and then we're just subtracting the pieces.
Okay.
So 134 with a loss of methyl, methyl's 15, so 134 minus 15 is 119. Here where you're losing an ethyl, ethyl group is 29, 134 minus 29 is 105. Okay. Any other questions on those? Okay, then let's look at something. Call your attention to something. Do you see how in this spectrum you have your molecular ion, 134, and then you have a little tiny peak 1 unit above? That's not unique to sec-butylbenzene. Let's go back and look at a few of these others. You've got the molecular ion, and then you've got that one little peak 1 unit above. Molecular ion, the peak 1 unit above. All of these have that. By the way, we call that, so the molecular ion, as we've talked about, we will typically refer to it as, it's abbreviated oftentimes as M+. Because that little peak is 1 unit above, we're going to refer to that as, not surprisingly, the M+1. Okay, it's just 1 unit above the molecular ion. So what is that? Why do we keep seeing that in all of these mass spec? If you think about it, all these molecules so far have been hydrocarbon. So if you think about those masses, hydrogen is a mass 1 atom. Carbon is, what? 12, mostly. Right.
If they're picking up a hydrogen, would they still be charged?
Well, it's not picking up a hydrogen. that one unit above is actually corresponding to the carbon. Because remember, carbon, the vast majority of it anyway, in the universe is C12. Right? About 98.9% of the naturally occurring carbon atoms are carbon-12. But there is a little bit, 1.1% of all carbon atoms that are not carbon-12. They are carbon-13. And so that little peak, that's this M+1, is actually from C13 incorporation. Right? So because mass spec is dealing with atomic masses, you will pick up isotopes when there are isotopes.
So what you're saying is just there's one carbon in the molecule that's a carbon-13?
Mm-hmm.
Okay.
Yeah. And depending on how many carbons you have in your molecule, you'll get different size M+1s, but they're typically very, very small. Right? What is, so think about that in the context of a heteroatom. So let me do a thought experiment with you. Let's say we were dealing with chloromethane. Right, so what would the molecular ion of this molecule be? Well, carbon is 12 primarily. You'll have an M+1 obviously because anything that's carbon-based has an M+1 due to C13 incorporation, but let's focus on the actual molecular ion. So carbon is 12, hydrogens you've got 3 times 1. What is chlorine? Fortunately, we have a periodic table here. The periodic table tells me that it's 35.45. So are we going to see a molecular ion of 50.45 here?
That would be with just the radiant carbon 12.
Yeah, just the C12. Would we expect to see a peak at 50.45? It would be kind of difficult. I mean, if you look at the scale of mass spec, you're dealing in integer values, right? Nowhere have we seen a fraction or a decimal on any of these peaks. The answer is no. We're not going to see that. Why don't we? Mm-hmm.
Because that 35.45 is an average.
Yeah.
Chlorine's either going to be 35 or 36.
Mm-hmm. Exactly. So remember, that number that I'm getting off the periodic table is not the atomic mass. It is the average atomic mass. It is an average, actually the weighted average of all naturally occurring isotopes. There is no chlorine that weighs 35.45 AMU. Chlorine either weighs 35 or it weighs 37. So you're going to see a peak not at 35.45, but you're going to see a peak corresponding to chlorine 35 incorporation or chlorine 37 incorporation. So this, because the peak is 2 units above the molecular ion, is what we would refer to as M+2. And it turns out this can be quite useful. The presence and the size of this M+2 is very diagnostic for heteroatom incorporation. So different heteroatoms are going to give you a different pattern of the molecular ion relative to its M+2 peak, based on the amount of naturally occurring isotope. Okay? So for instance, if you look at chlorine, chlorine is approximately 75%, 35. and about 25% chlorine 37. And so what that means is if you looked at a spectrum of something that contained chlorine, you would have the molecular ion, and then about a third the size of the molecular ion, you would see a little M+2. And that pattern, again, is highly diagnostic, which is very, very useful to us because, as I think I mentioned last time, heteroatom incorporation is very difficult to detect by other means. You know, if you took the NMR of a chlorine-containing molecule, you're not going to know that there's chlorine. I mean, you'll see some deshielding due to it, but lots of atoms cause deshielding. If you take an IR of a chlorine-containing molecule, you're not going to know chlorine is there because there is no carbon-chlorine bond absorption. Well, there is, but it's deep in the fingerprint, covered up by everything else in the fingerprint. So there's really no diagnostic peak that would give you any indication that you have a chlorine in your molecule. So absent mass spec, it's kind of difficult to tell when you have these heteroatoms. And mass spec gives us a very reliable way of seeing that. Right? So a couple of the ones that you need to know. So actually, here's one. You can see this is a sulfur-containing molecule because sulfur has an M+2. Most sulfur is 32, but about 4% of it or so is sulfur 34. You can see that in this spectrum, you have the molecular ion that's corresponding to sulfur 32. You have a small M+1, 1 unit above, which is due to C13 incorporation in the molecule. And then almost just a little bit bigger than the M+1, you've got the M+2, which is due to sulfur 34 incorporation into the molecule. Okay? So there's 3 common ones that you need to know about. And those are going to be the sulfur, we just talked about. You need to know chlorine, where the M+2 is about a third the size of the molecular ion. And then the bromine is really quite distinct because bromine has 2 isotopes that are present in equal amounts. And so what that means is your molecular ion is the same size as the M+2. So it looks like a doublet. All right, so let's have a look at a couple of these, what these actually look like in spectra. So here's one containing bromine. So you can see that you've got the molecular ion here labeled in blue. You have an M+1 of it due to carbon 13 incorporation here. Then you have the M+2 that's roughly equal size. And then you have this other little one, which I guess you would consider the M+1 of the M+2, right? C13 incorporation into the bromine 81 containing molecule. Okay. Any questions on that?
So say if there was a chlorine in that compound, right, would there be an M+3 or?
You would see another kind of doublet because you would end up with a peak that would have bromine 79 with, actually, you'd get the bromine, a peak of bromine 79 and chlorine 35. You'd have a peak bromine 79 with chlorine 37, bromine 81 with chlorine 35, and bromine 81 with chlorine 37. So it would start to get a little bit complicated.
So, but is M+3 a possibility? Like, does that occur in these type of graphs?
+3. No, I can't really think of a case where you would end up with an M+3. Yeah. Okay, so, and then finally, you can see there's one of the chlorines, and you can see that the M+2 here is about a third of the size of the molecular ion. All right, so let's go ahead and look at the last, I think we've got 3 functional groups. The last of these 3 functional groups are gonna all exhibit a similar and new fragmentation pattern. The first of these are the alcohols. And the last 3 of these, the alcohols, the amines, and the carbonyls, are gonna exhibit this new common fragmentation style, right? And this new fragmentation style is what we call alpha cleavage. And so when we're talking about alpha, what we're referring to is, and you're going to see this used quite a bit, you have a carbon of interest, and that carbon of interest is oftentimes a carbonyl, or it's a carbon that bears a heteroatom. So that is our carbon of interest. And then we count back from that using the Greek alphabet. So there's an alpha position, there's an alpha position. That would be a beta position, that would be a gamma position, and so on. Right, so it's not an IUPAC thing, it's just kind of, I don't know, they've just done it forever and you still see it a lot. But in any case, what we're going to be doing with these alpha cleavage is cleaving the alpha bond. So you can see in this particular example, we're cleaving to the right of the carbon bearing the heteroatom. You can also cleave to the left. Both of those would be alpha cleavages. Now, why is that important? Why is that useful in terms of a stable carbocation? Well, here again, with these types of functional groups that involve oxygens and nitrogens, I know what electron I'm going to lose. Because I have 2 different types of electrons. I've got the electrons of the sigma bonds, and I've got the lone pair electrons. And lone pair electrons are much less tightly held. And so when you subject this to the high energy beam of electrons, I know I'm going to lose one of those lone pair electrons. And it's kind of hard to see on the slide, but what is represented there is you've got the lone pair, nothing happened to that one, and then you have a dot with a plus there, indicating that one of the electrons of that pair was ejected. So you can see maybe why this would give us a good carbocation, because if you cleave alpha, again, that's going to be a homolytic cleavage. So we get something like that. That's going to give us a CH3 dot. And then you would end up with a, go ahead and draw it like this initially. You end up with a dot on oxygen and a dot on carbon, which you can kind of just bring together like we've been doing into a pi bond. So ultimately, what this results in, these alpha cleavage, they just generate, it's just another way of generating resonance stabilized cations. All right, and like I said, you can cleave on either side. So in the first one, we cleave to lose the methyl. And then on the other one, we would cleave on the other side, which would give us, in this case, the propyl. All right. Any questions on the alcohols, on these alpha cleavage? All right, let's look at an example maybe. We'll do, let's see, we've got the pentanol here. And if we do the alpha cleavage, we'd expect peaks at 73 and 45. So 88, we have a very weak molecular ion. And this is fairly characteristic of alcohols as well. Alcohols give very, very weak molecular ions. You can see at 73, we have a small peak here. And then the other one we were looking at was 45, which is the base peak. And again, the trend that we've been seeing all throughout is held here as well. Both of those alpha cleavage patterns shown here, but one of them is much stronger than the other. Right? That one, this guy here, is a much, much stronger fragmentation than the other one. And that's simply due to the radical. Right, that first one is giving rise to a methyl radical, and thus is not nearly as strong as the second one. All right. Okay, we can go through, I think I've got another alcohol here we can look at. So if we were dealing with this guy, the molecular ion we would expect is going to look something like that would be the radical cation. And then what we're going to do is just cleave to the left and cleave to the right. So if I cleave to the left, we lose the isopropyl radical. And that would be your cation. If we cleave to the right, we're going to lose the ethyl radical. We get that cation. So here we're dealing with a 102 molecular ion. Loss of the isopropyl would give us a 59 fragment. (102) loss of 29 to ethyl gives us a 73. So we can have a look and see what we can find. There at 102, again, these alcohols give very, very weak molecular ions. The 73 is fairly strong here. And then the other one, the 59, that's your base peak. Okay. All right, any questions on the alcohols? Okay, we got two more. We'll look at the amines. The amines are quite unique. And the reason why I say that is because if a molecule has a nitrogen incorporated in it, it has an odd valence, right? So all these carbon-based molecules, carbon has an even valence because it can make 4 bonds. Well, nitrogen can only make 3. And so what that means, that gives rise to something that we refer to as the nitrogen rule. And the nitrogen rule states that if you have an odd number of nitrogens due to its odd valence, its molecular ion will be odd, which is pretty unusual. If you go back and look at all the spectra that we've looked at so far, everything had an even massed molecular ion. Again, because carbon has an even valence. When you start incorporating nitrogens, your molecular ion is going to be odd. But these are going to cleave in much the same way that we saw for the alcohols because they contain a lone pair. And so when you hit these nitrogen, these amine containing molecules with the high energy beam of electrons, you're going to end up losing one of the lone pair electrons. So that's going to give rise to something that looks like that. And as a result, when you do those alpha cleavages, that's going to, again, give you a resonance stabilized cation. And so you can see in this example here that I have on the slide, I cleaved to the right of the amine, done the alpha cleavage to the right. So that gives this resonance stabilized cation, and it would give a ethyl radical. And the same thing on the other side. So let's go ahead and have a look and see if we can look at maybe a more interesting amine. So it's this guy. All right, so when this becomes the radical cation, it's going to look like that. And then we can cleave to the, there's a couple different ways we could cleave the left. So we could lose that guy, the methyl group. And then that would leave the cation looking like this. Probably not going to be terribly prominent because, again, we're getting a methyl radical from that. You can cleave that guy. And then you can go onto the other side and you can cleave the isopropyl. So notice that for this compound, the molecular ion is 129. Again, it's an odd mass because you have an odd number of nitrogens. Okay. So when we go to figure that, the fragment ions, 129 minus the methyl is a 114 peak. The 129 minus the ethyl, that's the math I can do actually, that's 100. And then the loss of the isopropyl would be an 86. So we can have a look at those. So we've got the molecular ion down here. Again, amines, just like alcohols, give fairly weak molecular ions. We've got the 114, that's fairly weak over there. Again, not unexpected because that 114 comes from a methyl radical loss. The 100 peak, fairly strong. And then the other one was the 86, again, fairly strong. All right. But again, with these nitrogens, you'll note that the numbers are kind of flipped, right? You have odd molecular ion, and any nitrogen-containing fragment is even, which is just the reverse of all of the hydrocarbon compounds. With all those hydrocarbon compounds, what you saw was an even molecular ion and odd mass fragments. All right. Okay, so we have one final functional group to look at, and these are the carbonyl compounds. And we're going to look at actually 3 different fragmentation patterns for these. The first of which is nothing new. It's just alpha cleavage. All right, so this is the same kind of fragmentation that we saw for alcohols and amines, and we do it for the same purpose. Because in a carbonyl compound, we actually have 3 different types of electrons. You have the electrons of the sigma bonds, you have the electrons of the pi bond, and you have the lone pair electrons. And they go in that order. Right? The sigma are the most tightly held, followed by the pi, and the lone pair are least tightly held. So when you hit this with a high energy beam of electrons, you're going to lose, just like the alcohols and amines, one of the lone pair electrons. So that gives me a radical cation that looks like this. And as a result, by cleaving to the left or to the right, doing those alpha cleavage patterns, that gives rise to a resonance stabilized cation. Okay, so for instance, if I had the plus dot there and you do a homolytic cleavage, what that's going to look like is so we could kind of put those bonds together, and a different resonance form is going to be that. Okay. But in the end, it's the same as we saw with the oxygens and the alcohols and the amines. They do these alpha cleavages to give rise to the resonance stabilized cation. The other thing that these can do, they can undergo secondary fragmentation, meaning once you make this type of ion, you can simply lose carbon monoxide as a stable small molecule. And so you can do the alpha cleavage, get to something like that, and then this guy can just lose carbon monoxide, and it would give you the 3-carbon cation. And I think where we'll end today is the third and final way that these can cleave. And this is an interesting rearrangement known as the McLafferty rearrangement. Now, a note about the McLafferty: you can only do this when you have at least one gamma hydrogen. All right. So again, to kind of use that style of naming, you identify your group of interest, which in this case is the carbonyl, and then you count back from it using the Greek alphabet. So this would be an alpha position, that would be an alpha position. That would be a beta position, that would be a gamma position. So you can see in this structure you have one gamma hydrogen, which is a requirement for this special rearrangement. So what I want to do is walk you through kind of the arrows here.
Did you say it was at least one gamma hydrogen or only one gamma hydrogen?
At least one, yeah. So let's go through and see if we can figure out mechanistically what's going on with this McLafferty rearrangement. So this starts, this is actually a polar reaction mechanism. So we're not doing radicals, we're dealing with a lone pair. All right, so let's see. There's my alpha position, there's my beta, there's my gamma, and you can see that you do have that one gamma hydrogen. And that's how this thing is going to start. This thing is going to start as the lone pair on the oxygen reaches over and takes that gamma hydrogen. So let's just draw an arrow that represents that. So if that occurs, the electrons of the gamma carbon and hydrogen bond, the electrons of that bond have to go somewhere. So they're going to end up getting pushed into the beta carbon. So essentially what that arrow is showing is you're making a double bond between the gamma and beta carbons. Well, if that happens, then the electrons of the alpha beta bond have to break. So they're going to go here as that bond breaks. And then the electrons of the pi bond to oxygen are going to go onto oxygen. So what all of this circuit of electrons results in the end, is, let's see, I'm going to draw the right-hand part first. So you have these two methyl groups that were just along for the ride. They didn't go anywhere. They're connected to the gamma carbon. The gamma carbon is now double bonded to the beta position. So it ultimately gives me a neutral alkene. Now, this one, remember, I don't see this. I don't see it in the spectrum because it's a neutral molecule and you don't see things that are uncharged in the mass spec. So this occurs, but I don't see it in my spectrum. The thing that I will see is the other half, the left-hand part of the molecule. So I'm going to draw it like this. That would be an alpha position. The carbonyl now has a double bond to it, and this guy is now a single bond to oxygen and now has an H attached because that's what began this whole thing. That is my McLafferty fragment. And these are typically quite strong peaks. The other notable thing about the McLafferty fragment, because it all began with the hydrogen abstraction, is these will always be even massed fragments. All right. Any questions on how we did that? Okay, what I'd like for you to do is see if you can do one. So let me give you a carbonyl compound and then see if you can predict the McLafferty fragment for it. So we know the electron is going to be lost. Actually, I'm going to do it over here. Here's one of the oxygen lone pairs. So first off, can this undergo a McLafferty rearrangement? To the left, you have alpha and beta. So you can't do it from the left-hand side of the carbonyl. From the right, alpha, beta. You actually have two gamma positions. So in theory, you could get two different McLafferty rearrangements on this. In practice, it's not going to make a difference, because the only difference whether you took from gamma carbon here or gamma carbon here is going to be in the nature of the alkene. The cation part is not going to change regardless of whether you pull from here or from here. And the cation is all you're going to see. So yeah, it does make a difference technically. You get a different alkene part, but you don't see the alkene part in the spectrum anyway, so it kind of doesn't make a difference. But for the sake of mechanism, pull from this methyl group here. See if you can draw the McLafferty rearrangement pulling from that methyl group. So take just a minute and see what you can come up with for that. How's it going? Feel pretty good? All right, let's see if we can figure out how these electrons flow. So remember, the first part of all of this is going to be the lone pair on the oxygen grabbing the gamma proton. So that would be lone pair grabbing that electron. The electrons of that bond have to go somewhere, so they will get dumped into the beta position. That's what's going to form your alkene, ultimately. So if you're making a new double bond between gamma and beta, that's going to ultimately serve to break the alpha-beta bond. So the electrons there end up going into the carbonyl and ultimately back up on to the oxygen.
Why does it choose to break the bond between the two carbons rather than just popping off a hydrogen at that beta position? It seems
So, like, just losing a hydrogen here?
yeah.
Well, what kind of, think about leaving group ability. What kind of leaving group would H minus be?
I'm not very good at
Yeah.
this.
Whereas if it loses this, you know, this whole chunk, it's losing a highly resonance stabilized chunk. I mean, this thing is, once it grabs the proton, it's already, it's kind of a positively charged species, right? And so that it's kind of the same story of, think about when you were learning those basic reactions, you know, like something like that. Before you could ever think about losing the OH group, what did we have to do?
Protonate it.
You had to protonate it, make it a positively charged leaving group. So that's kind of what you're doing here, right? You by the oxygen grabbing that proton initially, it's becoming a positively charged species.
It's a ginormous water.
Yeah, kinda. Yeah, it's just making a giant complicated leaving group that is ultimately detectable in the mass spec. So then, in the end, once we follow all those electrons through, let me go ahead. I'm just going to draw my alkene part first. So you've got the gamma, which is now a CH2 group, and it's double bonded to the beta, and then whatever else is attached to it doesn't really make a difference. It's just that ethyl group that was just along for the ride. Again, you don't see that because it's a neutral small molecule. What I will see is I've got, starting from the left, beta and alpha and carbonyl. And then that's double bonded to the other alpha. This guy is O, now bonded to H and plus. Okay. Any questions on how we did that? So again, these McLafferty fragments, they're going to be even massed and usually quite prominent peaks in carbonyl compounds. Okay, well, I think that's probably a good place to stop. So what I would propose, we have to do synthesis today, right? Yeah, okay. And y'all all got your assignment last time, right? For the one that you have to put up on the board. So what I would propose is that we stay in here and do synthesis. Actually, let me check and make sure there's nobody coming in after us. Yeah, we're good. So why don't we stay in here,